Good morning. I am Karthik Chanupati and this is my presentation on Lab 4. In Lab 4, we were required to analyze the motion of a spring mass system that was undergoing oscillatory motion. We had to compare the results obtained from the computer model and the tracker model and notice if there were any differences. The main physics formulae used in this case were Newton's second law, which states that force equals mass times acceleration, and spring force, which was equal to negative kx, where k is a spring constant and x is the change in the length of the spring. Physical model. So for physical model, I took multiple reference points in the tracker model and used it to get a graph about the motion of the spring mass system. And from that, I was clearly able to observe that it was in oscillatory motion, and we can notice it by looking at its displacement in the x-axis. Computational model. So for the computational model, the first thing that we need to observe is the change in energy versus time graph. And here we can observe that there is no energy created nor lost in this scenario, which clearly proves that the object was undergoing harmonic motion. And when we compare the computational model and the physical model, we can observe that there is more displacement in the computational model than in the physical model. It's probably because it doesn't take into account changes in energy, air resistance, and a few other factors. And now, when we look at the code, the main aspects that we used were kinetic energy, which states that K equals half mv square, the potential energy formula which states that which is equal to mgh, h being its displacement in the y-axis, g being the value of gravity which is 9.8 meters, acceleration due to gravity which is 9.8 meter per second, and the mass of the ball, and the spring potential energy which is half ks into s square, where ks is a spring constant, and the total energy is the kinetic energy plus the potential energy plus the spring energy. And those formulae were used in order to determine the net changes in energy. And we also found out the change in the ball's velocity using Newton's second law, which is observed here. Is the energy principle satisfied? Yes, I think the energy principle is satisfied in this experiment, and this can clearly be observed by comparing the graphs of the oscillations of both the physical and the computational model. And when we look at the computational model, we can see that energy is neither created nor destroyed, and since there is no net change in its motion, and the same can be said of the physical model as well. So I believe that the energy principle is completely satisfied in this experiment. The oscillation period. The oscillation period in the x direction is 0.76 seconds, and the oscillation period in the y direction is 1.425 seconds. This is because in the experiment that we have considered, there is motion in both the x-axis and the y-axis. Thus, we get different oscillatory periods in both directions. Thank you for your time, and I hope you enjoyed this presentation.